Hello everyone, this is Hadi. Today we're gonna build a logistic regression classification in Scala using Spark machine learning package. And we're gonna write our code in Zeppelin notebook, which is similar to Jupyter if you write code in Python. Um, and it supports Scala. This is the very major difference, but it has other differences as well. So let's see how to set up Zeppelin Notebook first on your laptop. You can also have a cluster like Google Data Park Cluster or AWS EMR Cluster, or I assume also Azure has it. So you can run the Zeppelin on your cluster and write code and do computations in parallel on the cluster that you have. So here I'm just doing it on my laptop, which is a MacBook. If you go to zeppelin.apache.org and you click on download Zeppelin, then you can download this binary package that comes with Spark. And if you go to installation guide, there are other interpreters that come with Zeppelin. You can install all of them together, or you can pick the ones that you want. I just installed Markdown as well, but if you need other things, you can install them too. So once you do that, you need to go to the folder that you have downloaded. So Zeppelin folder that I have just downloaded, and you can start the daemon. If you click, if you enter, it starts. It takes a few seconds normally. So yeah, by the way, you have to go to localhost 8080 to see the Zeppelin notebook. Oh, sorry, localhost 8080. Let's see. There is this red dot here. Oh, it's now green. It started. So you can either import a node here, or you can create a node here. I've already created a node, so I'm just skipping these steps. So I just jump to the node that I have. We can go over that. So let's have a quick introduction to Spark ML. So Spark ML came after Spark ML lib package. Spark ML lib works with RDD as the input, as the data structure that keeps the data, versus Spark ML works with data frames. These data frames are similar to pandas. If you work with Python, similar to pandas data frames. They're easy to slice and dice in general, and they're more efficient in terms of time and space. But both of them are good to know, because sometimes, in my experience, sometimes you need to work with RDDs because of some special operation you want to do on your data. Oh, something just happened. Yeah, okay. So, but in this tutorial, I'm mainly working with Spark ML, but at the end, I'm gonna also work a little bit with Spark ML Lib. There are a few basic concepts in what was here that is missing now. It's weird. I don't know what I had here. Looks like something just happened to my notebook. Interesting. Yeah, okay. So the first thing is data frame. So data frame is a columnar data structure. Each column has a type, integer, double, string, etc. And we keep the data in that format, and then we transform data frames from one to another. So, and a transformer is an algorithm that transforms a data frame from to another data frame. And normally this transformation is in the form of adding one or more columns to the data frame. An estimator is an algorithm that first needs to be fitted on a data frame, and once fitted is a transformer. And a pipeline is a chain of multiple transformers and estimators together. We'll see how they work in this example. And for this example, I have manually created a small data set. It's in CSV format. It has columns ID, income, state, gender, owns car. So like the first one is saying that the income is $40,000, state of California, it's male, and he doesn't have a car. So let's read in the data. And by the way, I'm assuming you know some basics of Scala programming in here. It's not hard to learn it, and you can quickly search and find a tutorial on YouTube if you don't know the basics. So this is loading. So now the data is read in, and we call it data. This is a data frame. Let's see how many data we have. So we have 13 rows in that data frame, and these are the column names, ID, income, and so on. Let's check the schema of the data. So you see ID is string, income is string, and so on. But everything is fine if they're string. I mean, owns car is not string, is Boolean, but for now we are fine with that. But income is string is not desirable because we want to have it as a double or integer. Double is more preferable, I would say. So let's change it to double. So in here, I'm creating a new column called income double, which is storing the cast of income value. So I cast that income to double type and store it in income double. And then I'll drop the original income column and rename the income double to income. So this way I'm making it a double. So if you now, so I rename this to, I name it the new data frame data df. So if you look at that, you see income is a double now. You can take a look at 3 rows here. Like these are the ones that we just saw. So California male doesn't have a car, 40,000 income. Or this one, Utah female has a car and 35,000 income. So our goal is to predict car ownership using the features that we have. So owns car is our response variable, and we have state, gender, income as our features. Income is a continuous feature, and state and gender are categorical features. So we first need, so generally our models work with double values. So everything, even the label, even the response variable needs to be in double value, so in double format. So we need to map owns car to double value. So we map true to 0 and false to 1, or vice versa, it doesn't matter. And for this purpose, we will use a transformer that, it's not a transformer initially, it's an estimator that once it's fitted is a transformer. It's called string indexer. So let's see how it works. I'm defining a string indexer. It takes input column, which is owns car, and we name the output column owns car index, and we fit it on the data that we had. And once it's fitted, it's a transformer. Let's see. So I can use this label indexer, which is a transformer right now, and transform data frames, like the original data frame that I had. I can just do the transformation there and look at the columns and then the first 4 rows. So these are the columns. As you see, this column is added, owns car index. And you can see the data, what is in that column. So 1 is representing false. Again, 1 is representing false. Here 0 is representing true. So this has mapped true to 0 and false to 1. Now getting back to features. Let's start with our categorical features, which are state and gender. For categorical features, regression or logistic regression cannot work with strings as values. So it works with double values. And for that, we need to create, for each category of a categorical variable, we need to create a dummy variable. But this is not precise. It's not that for every category we have. For, like, if you have 10 categories, for 9 of them you have to create a dummy variable, dummy binary variable. For the 10th one, you don't need to do that. If those 9 values are 0, it means that the 10th one is happening. So, and for doing that, we will use one-hot encoder on top of string indexer. So let's see an example how this works. So I am creating a dummy, some data frame here with 2 columns, ID and category. And then I'm defining a string indexer that works on category column and outputs category index. And then I define this transformer, that a one-hot transformer that takes category index as input and outputs category vec. Let's see what's the result. So as you see, the first 2 columns are from the data frame that I just generated. And then the category index is the output of string indexer. So A is mapped to 0, B is mapped to 2, and C is mapped to 1. And category vec is mapping 0 to this dense vector. This is, I'll get to that. This is a dense vector representation. And so on. Let's see first what was the purpose here. So the purpose here is that you see category has 3 categories, A, B, C, 3 distinct categories. So it will create 2 binary dummy variables. So since it was 3, 3 minus 1 is 2. So, and it will look at the frequency. So A is the most appearing one here, then C, then B. So it will create category A dummy variable and category C dummy variable, and it will put them together in a vector. But as you see here, always at most one of these values is 1. Either all of them are 0 because B is happening, like in here only B is happening, so none of these binary variables are 1, or at most one of them. If A is happening, this vector should be 1, 0. If C is happening, this vector should be 0, 1. So, and that's exactly what this category vec is representing, but it's representing it in a dense way. So A is mapped to this, which means that it's a vector of length 2. At position 0, the value is 1. It's exactly this vector. Similarly for C, and for B, it's saying that it's a vector of length 2, and in no position it has any non-zero value, so it means it's all 0. And this is the similar method that is used in other languages like R. So the number of categories that you have -1, you create dummy binary variables, and then you input that one into the regression. So let's see how it works on our categorical variables. We have gender indexer here, which is a string indexer, and a one-hot encoder that works with the output of the string indexer that we have. So just one note here, I am setting handle invalid skip here. So that means if you see like strange value or a new category, skip it. There are other options that you can have here. I'm just using skip right now, but there are other options. You will see that at the end, like you can keep it or you can throw error. Similarly for state, I'll define string indexer and 100 encoder. So now let's see how it transforms the data. So I'm passing the data frame that we had to the state string indexer, and then I'll take the output and feed it to the state 100 encoder transformer and see how it works. Let's first take a look at test one. Test one has everything that we already had in our data frame, and it just added state index. And you can see that like 0 is the index of California. Again, 2 is the index of Utah, and so on. Then let's see what happened after we had the 100 encoder indexer. So you see state vec is added, and like here 201 is saying that it's a vector of 2. At position 0 it has value 1, and so on. Similarly for gender indexer and gender 100 encoder, we can run them on our test data, test 2, and then feed it to the 100 encoder and look at the column and the first row. So you see gender index and gender vec is added, and we have gender index, which is 0, and gender vec, which is a vector of length 1. At position 0 it has value 1. So gender, we had only 2 genders, male and female. So 2 categories, so we need only 1 dummy binary variable. And that's why this vector has length 1. And if it's 1, it means that it's male. If it's 0, it means that it's female. So now we're gonna get to the final parts of this these estimators and transformers that we are defining. Note that our models work with like one column as the column of all features, and because of that, we need to put all the features together. So our features are state, California, binary variable, state, Texas, binary variable, gender, male, binary variable, and income, which is a continuous variable. So to put all of them together, we will use a vector assembler, which is a transformer. You can see the how it works here. So I'm defining the vector assembler. Input columns, I give income, state vec, and gender vec. You should put them all into an array. And then you name the output column name. I call it features. You do that, and now let's see. Remember, test 4 was after the gender 100 encoder. Let's see if we give this test 4 to this transformer, what happens. I'll look at the columns and the first row. So this features is added to the end, features column. And you can see the first row here, it's saying 40,000, which is income. So remember here they had income, the first one. And then saying 1, 0, which is the state vector. And this is 1, which is the gender vector. So I put them all together. So, and you guys know that normally we do some normalization on the continuous features that we have. There are different types of normalizations. For the sake of this tutorial, I'm just sticking to this scalar, min-max scalar transformation. So I'm gonna map the values of income column to 0 and 1, which is the default min-max scalar transformation. But you can define your own min and max. So in here, I have a min-max scalar. I say get the features and scale them. So it will consider each entry, each position of the vector as a feature. So it will look at all the rows, the first entry, and scale them to 0 and 1. And then it goes to the second entry, all rows, look at them, and then scale them to 0 and 1. So you need, so this is an estimator first. You need to fit it on a data, and then it will compute the summary statistics first, and then it will become a transformer. So if you do that, you can then transform the data that you have. I'm fitting on the same data and transforming the same data. This assembled, remember, is coming from the feature assembler transformation. So I'm doing that, and I can look at the columns, and I'm also pruning other columns. I'm just keeping the features and scale features column. Let's see. You see, the first column, which is the income, 40,000, 50,000, and so on, is mapped to 0.2, 0.3, 0.15, and so on. The rest of the columns, each one was already a 0, 1 column. It was already binary. So when you map it to 0, 1, it's going to stay the same. So it's not changed. So this is 1, here is 1. This is 0, here it is 0, and so on. Just remember we had dense vector representation. So this is saying that it's a vector of 4, length 4, at position 0, it has value 35,000. So now we can define our logistic regression estimator. It takes in the label column, which is owned car index here. In our case, you remember it takes double values only. Features column, we're passing the scale features. Set max iteration, we're setting it to 20. Practically, I mean, by experience, I feel like 20 is good enough for most use cases. This is, so, you know, the optimization algorithms that are running to find the optimal coefficients for the regression, they're iterative optimization algorithms, and for those algorithms, normally they might not converge soon enough, or they might even be diverging sometimes. You have to set this max iteration to make sure that the problem stops in a reasonable time, the algorithm stops in a reasonable time. And set a regularization parameter. This is for avoiding overfitting. I'm not going to go into details. I'm just going to tell you guys how to build the pipeline in general. ElasticNet param is for determining what type of regularization to be used. If you set it to 0, it will use L2 regularization. You can set it between 0 and 1 as well. So let's create this estimator. Now that you have this estimator, you can create your pipeline. So your pipeline has stages. Determining the stages here. Gender indexer, gender 100 encoder. Similarly for state and state indexer and state 100 encoder. And then feature assembler, scalar that we define, then label indexer, and logistic regression. Yeah, you know, the order of these are important, but they don't have to be like all of them in this order. Like this gender indexer has to be before the gender 100 encoder, but like this one could come like after the label indexer. It doesn't matter. Or label indexer can be at the beginning or anywhere in the middle in here. But this LR has to be at the end because we are like working with the features that like LR has to be after the feature assembler at least, and this feature assembler needs not even after that one, after the scalar, because feature assembler feeds to the scalar, and then yeah. So the order is because you have to see like which one is taking the output of the other, the output column of the other one, and as the input column. This will determine the order in general. So let's define this. Now we are gonna train our model. So we are doing a train test split. This is pretty standard. Some people do cross-validation, like k-fold cross-validation. We'll get into that in other tutorials, how to do it. But for simplicity, we're just gonna skip that one and just let's go with train test split. We'll train on train portion and then evaluate our model on test portion. So I'm doing a split here. These numbers are just to make sure that the test part has enough rows, but normally I instead of 65, I make it 70 or 75%. Let's see how many rows we have here. 8 and 5, which is good. 8 in train and 5 in test. Let's train our model. So you see pipeline here. The pipeline that I defined here is it's an estimator at the beginning, especially because of this LR, because LR is an estimator. I didn't fit it on any data. So now now that it's fitted, it becomes a transformer, and it is a model. So I mean, it's a pipeline model, in fact, to be precise. So we can make predictions using that model. You can say model dot transform. Now I'm making the predictions on the test portion, and it will make predictions. So this transform here is adding some columns to test df, and those columns, if you look at them here, you see those columns. So everything up to here is what we expected from the pipeline that we already had, and then these last ones are the ones coming from that transform that I just called. So raw prediction, probability, and prediction. Ignore raw prediction for now. Probability and prediction. So these are the two. So this is probability, which is a vector. This is saying 53. 0.53 is the probability of index 0 happening. This is saying 0.46 is the probability of index 1 happening. So since the probability of index 0 is more, our prediction is going to be 0, index 0. And index 0, remember, was representing true. And in fact, we have true here as the car ownership. So this is a correct prediction. If you want to see what was your what is a 0 here, so which one is it representing, true or false, you can look at the label indexer that you used. So true is at label 0, so this 0 is representing true, and false is at index 1, so 1 is representing false. Let's look at more rows. The first row we saw, so I'm pruning other columns, just keeping these 3 columns. So the correct answer is false. He or she doesn't have a car. The probabilities are saying that the first probability is 40%, the second probability is 59%. So 1 is going to be the prediction, because this is higher. So and its index is 1. And 1 was representing false. So this is a correct prediction. Here you see this is false, but this is 0. It's a wrong prediction, and which is understandable. Models are not perfect; they make mistakes. And actually, if a model predicts everything correctly, you have to be worried a little bit sometimes. So let's evaluate our model. So for evaluation, I'm using the ML packages evaluation binary classification evaluator. And the only catch is that it only supports area under rock curve and area under PR curve for now. But for other metrics, we'll fall back to MLlib. Remember at the beginning I said we'll work with RDDs and MLlib. We'll see. So you need to pass the label column, which is Owen's car index, and then you pass the raw prediction column, which is probability. Be careful about here. There are other models that you pass like prediction or other columns, but for this model that we have, you need to pass probability to get the right answer, and you name the metric. Let's run it and let's see what is the area under rock curve. So it's 0.83, which is not bad, but we can always compare it to the AUC of the train data itself and see if it did any overfitting. So I'm making the prediction on the train data itself and looking at, so you see the first row is here. This is predicted 0, but it's actually false, so this is a wrong prediction. And this value is the AUC ROC of our model on the train data itself. So this is 0.8, this is 0.83. So it's good. It's a good, I would say in general, it's a good model right now. But if you see like this is way bigger than the test AUC ROC, it means that you're overfitting. But in general, since the data that I have manually crafted is very small, this is not like a good model in general. You have to have more data points. So for other metrics, you can right now use MLlib package. So for doing that, I need to extract the score and labels. So I go over the data frame, like train predictions that I had above. So remember this, yeah, this is train predictions, which is coming from the transformation of train data frame with the model. So I look at that data frame. I just pick the two columns, probability and Owen's car index. I create an RDD and then map each row to, so since this probability is a vector, I'm just picking the second index of that vector, and I'm also picking the whole values in Owen's car index. This one is actually doing nothing. So I do this map, I create an RDD. Similarly for test predictions, I'm doing this. I mean, I'm not, I said I'm not, I'm doing nothing. I didn't mean that actually. I mean like this is like just creating a tuple. The first value is the second index of probability vector, and the second one is just the value in Owen's car index. So I just created these two RDDs, one for train predictions, the other one for test predictions. Now in MLlib package, I am using binary classification metrics. I pass those score and labels RDDs to create those objects. Once you create those objects, you can now call different metrics. Just to double check with the above results, I'm calling area under rock. You see 0.8 for train, 0.83 for test, which is matching our previous results. I can also get the rock curve itself. I'm looking at the first 5 points of the rock curve. So 0, 0, 0, 0.33, 0.2, 0.33, and so on. This is for the rock curve of train predictions. Similarly, you have the rock curve of test prediction. You can also get F1 scores by threshold. There are other metrics that you can get. I'm not gonna go over them. Let's see how to put everything together. I put everything together here in a function called train LR model, and I have pulled out those fixed variables so to make it cleaner. You see here the action for invalid flag. This is the one that I use in set handle invalid. Remember, in the string indexer, we are skipping that row if it's a strange value. You can also keep it or throw errors. So everything here is the same. So I'm getting all the data and then the label column, which is owns car in our example, getting the array of continuous features and categorical features as the input, and then outputting a model. So everything is the same. We have the label indexer and the string indexer 100 encoder for categorical features. Everything is as we discussed. The only thing is here, you see pipeline that I have, the pipeline that I have here, it only has categorical stages. It's not like I'm saying state, string indexer, state 100 encoder and like gender index, string indexer, and so on. I'm not naming them one by one. I'm just doing it more systematically here. So I'm defining this function to100 encoder, which takes a feature name, and it will generate a sequence of two values. The first one is two functions, or two transformers, I should say. The first one is string indexer, which is fed on all data, and the second one is a 100 encoder, which takes the output of this string indexer and outputs another column. So this way, I can just look at the categorical features. So these are categorical features that I get from the input. I will do a map for each of them and use this to100 encoder that I have just defined here. And once you do that, you can create all the stages, all those like pair stages, string indexer and 100 encoder for each categorical feature. Then you can just pass this categorical stages to the pipeline that you have. So you can define this, and at the end, everything is as before. I do the train test split and train the model on train portion. You can do the evaluation, other things here, print out things that you want, and then I'm outputting the train model. Let's see if it works. So this is the data frame that we had, this original data frame. Now I call this function that I just defined. So remember, all the data, we pass all the data. Owns car is the label column. So here I have all data, label column, continuous features, and categorical features. So I pass owns car and then continuous, then continuous features and then categorical features. Let's run it. So I trained the data and created a model. I call it train model. So you can now make predictions using that. So I make the prediction on the original data, see how it works. So, and you can see that everything is as expected. These columns are the original columns: state index, state vector, gender index, gender vector, all that up to raw prediction, probability, and prediction. And you can see here, this is the probabilities vector, so it's 0.22 versus 0.77. So index 1 is higher, so the prediction is going to be 1, and 1 is representing false. This is a correct prediction, in fact. All right, thank you very much. Please leave your comments or questions below, or send me emails if you have any comments. I would be glad to answer them. And please subscribe if you like the video. Thank you.